Yeah, can you see my screen?
Yes, yes.
Okay, yeah. So welcome to the first year session for the course Circuit Complexity Theory. So what we'll do is every week we'll solve some problems related to that week's assignment. And if the deadline of the previous week's assignment has passed, we'll also discuss problems from that assignment. Okay. So today, like since the week zero assignment is not ungraded, we'll first discuss that, and then we'll move on to some problems related to week one's assignment. So is that fine?
Yeah, yeah, sure.
Yeah. Okay. So first, let's recap what we saw in this week. So this week we saw some a few basic things. We saw the definitions of Boolean circuits and formulas and various notions of their sizes and depths. Okay. So recall there are multiple sizes: size, size star, leaf size, etc. We also saw Shaman's theorem, which says that most n-varied Boolean functions require a circuit of size at least 2 to the n over n. And by most, what I mean is that if you were to pick a Boolean function uniformly at random from the set of all Boolean functions of n on n variables, then with high probability, that Boolean function would require a circuit of size 2 to the n over n. And similarly, we also saw the Riordan-Shannon theorem, which says that most n-varied Boolean functions require a formula of size omega 2 to the n over log n. Again, by most I mean the same thing. Pick a uniformly random Boolean function with very high probability, it will have this property. Okay, so now let's look at some of the problems for week zero assignment. Let's start with problem 4 because we will end up using problem 4 in problem 1. Okay, so the fourth problem is how many internal nodes does a binary tree with n leaves have? The options are 2n plus 1, n plus 1, n, and n minus 1. So which of these is correct? Yeah, it's n minus 1. Yes, and the reason is the following. So the reason is the following. So suppose that the tree, okay, why is split tree? Is right, has S internal nodes, right? Then these nodes can have twice many children, right? Or rather will have, because it's binary. Okay, so now, so these nodes have twice many children, and so it might appear that we can just plug in twice many leaf nodes at these places, right? However, uh, every node except the root node must also be a child of some node, right? Since every node except the root node is also a child of some internal node, this means that so out of these two as many, uh, S minus 1 are other internal nodes. This leaves us with uh, S plus one many leaf nodes. Many additional children must be leaf nodes, right? So S plus one equals N. Yeah, this is this. Yeah, so is this fine? Yeah. Okay, so then let's look at the next problem.
One
Yeah.
thing. I had like another idea of proving the last question,
Okay,
but
yeah.
I'm struggling with how to put it formally. Like my idea was
Okay.
suppose like I'm going from leaves to the number of internal nodes. Okay.
Okay.
So suppose I have n leaves, and
Hmm.
since the tree is binary, so two leaves would have one parent.
Uh, okay, that's not necessary, right? Because consider this structure. Uh, so the red nodes are internal nodes, okay?
Okay.
And okay, so okay, okay, at least okay. So are you saying that every pair of two nodes will have a root, will have a same parent or
No, no, not
one pair?
same. At least one parent, or at
Okay,
most
right,
multiple,
then you
right?
are fine, right?
Right.
Yeah, then
Okay.
you it would work. So
Yes.
if at least one pair has the same parent, then you are fine. Yeah.
Yes, and now like the for when we consider the next leaf, so it
Hmm.
might be like the next two we how do I put it? Like now this parent would have uh, the now the this internal load we could consider, and one more leaf we could consider, and they two of them would have one parent, and this way like
Okay.
we can go upwards, and we would have like n minus one internal loads.
Okay. So but okay, so this can happen, right? That okay, the first pair of leaf nodes had a common parent, but
Yes.
so did the second pair of leaf nodes.
Either way we would have n minus 1 internal loads.
Right, but how do you proceed? So let's say you have
I worked it out. It works fine for obvious reasons. Suppose it's a complete binary tree. So
right.
we pair up each of the leaves, and they would have one parent. Then we pair up each of those layer of internal nodes. They would have one parent, and so on. We would go upwards, and it would be n minus one, obviously. Uh, that's like good case if we expect.
Hmm.
And another way it would be like we make the first pair. At least there would be one like two
Right.
leaves which have one internal node. Now we
Yes.
consider this internal node we just made, and
Right.
one leaf. We can have one parent for these two, and then next leaf with this internal node, and the next leaf with this internal node. So
Yeah, but so these are two extreme cases, right?
yes,
Like
yes.
in one case you
I'm
have a very skewed tree, in
yes,
one
yes.
case you have a full tree.
Yeah, exactly. I'm taking the two
Right.
skewed cases, and for both the results are n minus one
Yeah,
kind
for
of.
both, yeah, for both these individual cases, your argument would work.
Yes. So what my argument is like starting with two leaves, I have one parent,
Hmm.
and for each additional leaf, I would need one more internal node.
Oh, okay, so for let's say for leaf one and two, you need one internal node, right?
Yes.
Then for leaf three, you might need an extra internal node. That is true.
For every additional leaf, three,
No, no,
four, five, six, I would need one more internal node if I am to include them in the current tree. Like I'm constructing a tree starting from the leaf onwards.
right. So okay, now what I'm saying is consider this case. These are internal nodes. Okay.
Okay.
So now for the first two leaves, this is the parent you picked. For
Okay.
the third leaf, you need an extra internal node, right?
Yes, yes.
But for the fourth leaf, which node are you like counting it
No,
against?
no. Like I'm constructing the tree starting from the leaves, right? So,
Okay.
okay, first you draw the entire tree you are like talking about, and I'll show how I'm going to construct it.
Okay, so for this is a full tree. So for this, your argument would work. The tree I'm constructing is a full tree.
Yes. So, like for this Q tree, I would like the next leaf I'd
Yeah. So what I'm
pair
saying
up
is
with internal
your
node.
argument would work in both the extreme cases.
Yes.
What I want to understand is how would your argument work in some other case where
It
it's not skewed and it's not full.
it would work, right? But uh, okay, just give me a moment. So like I'm constructing the tree starting from the leaves, and I'm taking one leaf at a time, right? Since
Okay.
you want me to reach from this stage to a particular tree, right?
Okay.
Right. So if like this tree is skewed, which I can see, obviously know the final result I have to like go through. So what would I do? Like uh, attach the new leaf to an internal node, and then consider that internal node and the new leaf with that internal node, and go on, right? But suppose
Right.
I was to approach the tree structure of a complete binary tree, right?
Right.
So instead of, like, I pick the first two, made an internal
Hmm.
node, and now with the next two leaves I have to create a different internal node, right?
Right.
Right. So for the third leaf I would not like it attaches the internal node, but I would pair it with the next one, right? And so
Hmm.
now I have two internal nodes, and they would again need one more node, right? So
Right.
if I know the final tree I'm going to construct, and if the next leaf is supposed to be attached to the internal node or should be paired up with the next leaf, I can construct the tree, what I'm saying.
Okay. So wait.
I think I might try to write this like formally and then send it to you.
Okay.
You
So
might
like
look it over.
maybe one thing you can do is okay. So for the first two leaves, you okay. For the first two leaves, you have a common parent, right?
Yes, yes.
For the third leaf, uh, pick a parent
It depends.
and
It depends.
like for the third leaf, okay, you will have to pick a new parent, right? For the third leaf at least.
If like for the third leaf, at least I would have a new parent, and
Right.
the parent would be common to the last internal node or to a new leaf will depend on the kind of tree I'm creating.
Yeah, yeah, okay, so no, so I was just trying to rephrase your argument. What I was trying to do was,
Mhm.
for the first two leaves, you first two leaves are fine. For the third leaf, what I wanted to do was pick a parent, which was I think okay, try the deepest parent in the tree, and wait. Okay, so yeah,
I think you get the idea, but like it's difficult for me to like state it formally.
okay.
So,
Because what you're essentially doing is for every leaf, you are charging it against an internal node, right?
uh, yes, maybe.
That's
Like what I'm
that's one
saying,
way to
that
look at it,
a
right?
new internal node would be needed for
Right.
every additional
That's
leaf.
basically okay. So think of it like this: you like every internal node is a coin, and for every leaf you add, you have to pay a coin, right?
Right, right.
Yeah. So essentially, what you're doing is a charging argument. It's just that it would be much better if you can, for every new leaf you add, you can characterize exactly which node you are charging.
Okay. But
For
that would depend
example,
on the kind of tree I'm like I
right.
want
So
to get to.
right. So what you can do is okay, like okay. So for example, for a skewed tree, it would be the deepest parent. You can charge sorry, you can charge the deepest internal node, which is not full yet.
Okay, yes.
And for the full tree, what you can do is, so the full tree would look like this, right? These two are fine. You can charge them to a common parent. Then, okay, so this thing is as an empty child, right? Right. But that means that both of these have a parent, right?
Yes, yes.
Which is full. So in the case of full tree, what you are charging for the okay, so for these two, you are charging. Okay, let me draw it with a different color. For these two, you are charging this node. For
Yes,
this, you
yes.
are charging this node. For this, you are charging this node.
Oh, well, in a way, yes, yes, we can say that.
Yeah. So, like one way to make your argument formal was to somehow like characterize exactly which node you are charging in terms of the structure of the tree.
Uh, yes, I would have to show which
Yeah.
node exactly I'm charging.
Right.
Right. So
Yeah,
that,
that's one way. Like there might be some other way as well.
yes, but how do I go about it? Like it seems difficult now. You say that
Yeah.
I have to identify which node I have to charge.
Okay. Okay. You don't have to. That's one way to do it.
Okay,
I mean, there
well,
might
that's
be
the
some
only
other
way
way,
we have
right?
it right now. Like I would have to think some other way, but
Hmm.
okay, I'll try it, and like if I come up with something, I'll share it.
Yeah.
Like, I think we can move on to the next one.
Yeah. Okay. So the next problem is pick the smallest upper bound on the number of binary trees with n leaves, which is valid for sufficiently large n. The options are n factorial, 4 to the n, 4 to the n minus 1, and 2 to the n. So which of these is correct?
Now, well, the answer is 4 to the n minus 1,
Yeah.
but why?
Okay, so one simple way is this. So there are n leaves, right? These imply n minus 1 internal nodes. Now forget about the tree, just focus on one internal node, okay? For that, you have four options, right? Suppose this is the internal node. One option is both his children are leaves. Another option is the left child is a leaf, the right child is a same but flipped. Now, okay, so over here the nodes aren't labeled, right? So it doesn't matter which internal node you pick as long as it's just an internal node. So the only distinction is internal node versus leaf, right?
Yes, yes.
So these are the only four options. If if the internal nodes were labeled, then yeah, you would have many options.
Yes, we could like have factorial of that many arrangements of those
Right.
internal nodes.
Yeah, but since over here any internal node is like completely every internal node is completely identical, these are the only four options, and you have these for n minus one internal nodes, right?
All right, one thing,
Yeah,
the two options in the middle, the leaf, internal node, and leaf, they
right.
are like, do we have the notion of left child and right child in these trees?
Yeah, so if you don't have the notion of left child and right child, then these two trees would be similar, right?
Well, the options in the two would be actually the same option for an internal node.
Okay, so so if you don't have a notion of left and right child, then these two would be the same. So I think over here we do have a notion of left and right child.
Okay, and one
Yeah.
thing, in these two questions, when it said binary trees, it is must that each internal
Yes.
node should have exactly two children.
Right. Otherwise, even with one leaf, there are infinity many trees
Okay.
because this is a tree with one leaf.
Well, you can extend it as long as possible.
Right. And so yeah.
With one leaf, it's exactly one. With two leaves, it's infinitely many, I think.
No, so even with one leaf, okay. So here there is just one leaf, right? This is a leaf. This is one leaf. This is one leaf. But they are different trees because they have different number of nodes.
Okay, since there's a root, then we have a leaf. Okay.
Yeah.
You consider the top one as root now. Otherwise, that would be also counted as a leaf, I think.
Okay. Yeah. 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 So the next problem is Suppose there is some randomized algorithm which makes two-sided error 1 over 4. How many times should one perform independent runs of the algorithm and take the majority to bring down the error probability to 2 to the minus n to the c, where c is some absolute constant? Pick the smallest value guaranteed to work. The options are 2 to the n to the c, n to the c order 1, and order log n. So which of these would work? Yeah, B would work. And the reason is just an application of Chernoff bound. So, okay, yeah. First, let me just assume that the algo is yes, I'm assuming that the algorithm is an algorithm for a decision problem because I think the only types of algorithm for you which you can boost are algorithms for decision problems, algorithms that output are that work for optimization problems. Yeah, so for search problems, I don't think you can optimize, like you can boost. Okay, so I'm assuming it's that the algorithm is for an for a language. Yeah.
How do you distinguish a search problem? I think it's a decision problem, isn't it? Right? Like,
So search
what are the
problems could
different
be like
problems you
this.
just know?
Okay, so one is a decision problem. Given an instance, decide whether it's a yes instance or a no instance. Okay.
Okay.
Another is a search problem. So, for example, uh, given a three CNF formula, find a satisfying assignment. That's a search problem, right?
Okay. Yes.
And then there are optimization problems. So, for example, given a three CNF formula, find the maximum number of clauses that any assignment can satisfy.
Maximum number of clauses any assignment can satisfy. Okay.
That's maximum overall assignments, number of clauses that can be satisfied by that assignment.
Yes. Yes. Okay.
So I think for the first problem, first type of problems and the last type of problems, you can boost probability because the answer is supposed to be a number.
Right. Yes.
Yeah, and I don't know of any way of boosting the success probability of a search problem.
Well, uh, since the output is supposed to be from a domain,
Right.
can't we like
Oh, but the domain can be used, right?
can be, but still there would be a probability distribution over the like outputs, and well, optimization boosting would mean like getting like improving the probability for some of the outputs, or like having.
Okay, okay, so okay, so one thing you can try is okay, so if you're a, just if you okay, so one thing that I was thinking about is this. Okay, so suppose you have an algorithm for here's one very simple algorithm for three SAT. Take an assignment randomly, check if it works or not. For such algorithms, if you run them for a large enough amount of time, the probability would improve, right?
Obviously, if there exists a
Right.
satisfying assignment.
Right. But this is just one type of algorithm, right? Can you do this for every type of algorithm that works for a search problem?
Well, then we would have to characterize like search problems more formally. So, like, since I'm saying that the probability should like improve, and we are like in decision problem, it's simple. It's a yes or a no. So we have like binary distribution of probability,
Hmm.
right? But with this, with other problems like both, I think search and optimization problem, we have say a domain and there's a probability distribution. So what would be the expected behavior of boosting? That would be a question, I think.
Okay, so yeah, okay, so one thing you can try is just run the algorithm multiple times and check if it satisfies the Yeah, okay, so one thing you can do is just run it multiple times. And okay, wait, for search, there is no notion of two-sided error. Okay, so okay, so for okay, suppose the problem is in NP, okay, so you can efficiently verify the solution.
Yes, yes.
Then what you can do is run it and verify the solution. And if its success probability is a certain amount, then it would work.
Let's say more than half or something.
Doesn't matter any constant. Inverse poly would also work,
Okay, yes, yes. Let's say inverse poly. So
right? So if your problem was in NP, then you can just repeat the algorithm multiple times and efficiently check if your solution is true or not, right?
yes, yes.
So for NP problems, this would work.
Right.
Yeah.
Okay. But like same thing won't be true for optimization problems, I think.
Okay, so for optimization, there is again, okay, so for optimization, it's much similar to just this decision problems. So ultimately, your answer is a number, right?
We'll say yes, we can say.
So one way to do is like take mean of the number, mean of all the answers you get,
Yes.
and then again take a the median of all of those. So there is okay, so there is something called means of median trick which works.
Okay. So, like, the question is the last one. Like, what are we expecting when we are saying that boosting a decision? Sorry, optimization problem. So, what I'm expecting?
Okay, so one thing is this, one notion is this. Your suppose your optimum value is opt, okay,
Okay.
and you have the guarantee that with probability epsilon, you are within delta of opt. So you are in 1 minus delta times opt, and okay, so 1 plus delta times opt and 1 plus delta times opt. Okay,
Okay.
you're in this range, right? Probability epsilon.
Okay, so what
Then
I'm
by
actually doing here, like with certain amount of approximation, I'm checking that with how much probability I'm achieving that. These,
right.
but like with delta amount of uh, uh, delta amount of
So
approximation
delta
to
is
the
your
objective.
approximation error, and
Yes,
epsilon is your probability.
yes, yes.
So
Okay,
over here, boosting would be okay. Suppose you have this epsilon delta guarantee. Give me a guarantee where the epsilon is to the minus n, something like that.
okay, yes.
So again, you would just want to boost epsilon, keeping delta the same.
So we can like I think have boosting for all three types of problems, right?
For 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 search problems in NPS,
Okay, for search in NP and like
yes.
yeah.
I mean, okay, but that's sort of redundant because we don't expect to have randomized algorithms for problems outside NP, right? So we expect BPP to be P.
We expect BPP to be sorry.
So we're believing that BPP and P are the same, right?
Okay, that would collapse P and NP and all everything, right?
Wait, how would BPP equals P collapse NP?
BPP contains NP and QNP both. I'm sorry, like
No, no,
it
no,
was
that is sigma 2P.
just a moment.
Yeah.
It's confusing. There is no relation between BPP and P as we know. Like if
Yeah, so far we don't know of any relation.
yes, yes,
Yeah.
okay. And what was at the intersection of NP and co-PP was co-NP was ZPP, where
Okay,
P
so
is a subset of ZPP.
no, no, okay, so the intersection of NP and co-NP is just NP intersection co-NP. The intersection of RP and co-RP is ZP.
Okay, okay. Sorry, sorry. Yes, yes.
Yeah,
It's okay. Yeah, PPP contains RP and co-RP both of them, right?
right.
There, I was getting confused.
Yes, yeah.
Okay.
Okay, so we are assuming that this is a decision problem, and now, okay, so I'll just do it for the case when X is in L. The other case is similar. Okay, and so um, x1 to x. Okay, now what we're going to do is output 1 if and only if x defined as their sum is greater than okay, is greater than t over 2. Okay, so this is the new algorithm. It just runs the old algorithm multiple times with independent randomness. Okay, so now what do we have? We have that uh, x1 to xn are IID, and sorry, x1 to xp. So we have this greater than equals to 3 over 4 because they're assuming x is in L and the error is 1, 4, right? Yeah. So now, okay, so here, let me write down sure enough now. Okay, let me call this x prime. So if IID 0, 1 random variables, then for so this is the Chernoff bound that we have, and we're going to use this. Okay. So in our case, we want to bound. So what's the bad probability in our case? Probability that so when would we not output 1? We would not output 1 if x is less than equals to t over 2, right? Okay, so now, okay, so what's the expected value of x? It's expected value of sum of I. So now what can I write over here?
uh, you can multiply 1 by 4 and 1 by 4 repeated times.
Why 1 by 4?
Sorry, what's represented by expected value of x here? Like,
Because expected value is just like the average of x, right? So it's so okay. Okay,
so
are you
x,
asking for the
like,
definition of expected value?
so x can be like 1 with probability 3 by 4 and 0 with probability 1 by
Oh,
4.
that is xi, right?
Xi can be that, right?
Right. So okay, so far we are at this step. What I'm asking is what can I write next? There is a sum of xi over here, right?
Right, but like we haven't stated sum over what, uh,
Okay, so it's sum over I in 1 to t, right?
1 to 3. Okay.
Because that's what xi's are.
Okay.
Okay, so you know the expected value of xi, right? Every individual xi you know.
Yes, yes.
That's 3 over 4, right?
Yes, yes.
So what we do? have is we have the expected value of all the individual x's. We want to find the expected value of their sum.
Okay.
Yeah, so like there is something called linearity of expectation which lets you like do this.
Okay, so that would be like just 3 over 4 times t.
Right. So yeah, over here you can use linearity of expectation.
Okay.
Yeah. Okay, so so now I know what expected value of x is, and over here I have 1 minus delta times expected value of x, right? So I want to find what delta is. So I want t over 2 to be of this form, right?
Yes.
Yeah. So t over 2 is 1 minus delta times 3 over 4 times t. This means I can cancel t out. I get 1 minus delta is equal to 2 over 3 if and only if, yeah, this uh, given by 2, 3, yeah. So delta is 1 over 3. So now I can just apply the bound, right? It's let one line below. E to the minus delta square is 1 over 9. Times expected value of x is 3 over 4 times t times 1 over 2, which is uh, e to the minus k times t. K is some constant, right? Actually, I can write it too. Yeah, so now we want, actually, I can use C, yeah, because C is a constant of this. So now, okay, so what are we interested in? We are interested in the error probability of the form 2 to the minus n to the C, right? So we want minus k to the, so yeah, we want kt to be equals to n to the C. So t is equal to n to the C over k, which is like order n to the C. So yeah, as long as we repeat it order n to the, okay, let me write this bigger. So as long as we repeat order n to the C times, we should get a disaster probability. Is that fine?
Yes, yes.
Yeah.
Okay, so why do we need to use Chernow bond exactly to arrive at this like conclusion? Why can't we simply see that like we need to the error probability to be like 1 upon 2 raised to the power n raised to the power some c, right?
Okay, so what you are trying,
Uh,
is this what you are trying to say? So x1 is correct with probability 1 over 2, 1 over 4. Same with x2, same with x3, and so on, right?
no, this proof is fine. Okay,
Okay.
I think am I audible?
Yeah, yeah. So what I'm asking is, what are you proposing? What alternative proof are you proposing?
Alternate like proof, uh, not exactly proof, but what is being asked that how many times do we need to repeat? What would be the
Right.
order of times I need to repeat this experiment so
Yes.
that the probability goes like 1 over 2 raised to the power n raised to the power c.
Right. Yes.
Uh, it is some inverse of an exponential function in terms of the input size.
Yes. The desired probability.
You're
Yes.
frozen, I think. Was I audible?
Yeah.
Yes.
Yeah.
Okay. So, and we see that like the error with one trial is 1 upon 2 raised to the power 2, something like that. So if I repeat
Wait. Okay. So what's the error with one trial?
1 over 4,
Right.
right, right. So that's like some exponent of 2, some constant value, right?
Yes.
And I want like the like it's 2 over 2 in the denominator, and I want it to be 2 raised to the power n raised to the power c.
Right.
So if I like repeat these experiments multiple times, this value would be multiplied by itself. The error would go down this way. So
If this were one-sided.
if this
So what
was
you are doing is the following. You are repeating it multiple times. You are getting x1, x2, and so on up to xt, right?
right.
Now what are you doing with these?
So no, what I'm saying that like for one instance I have some probability 1 upon 2 raised to the power something, some constant
Right.
value, right? And if I repeat like what I'm doing here, if I
So you
do
are
this,
repeating.
if I'm
That is
repeating
fine.
like n raised to the power c times, some order of that, some function of that, the probability would itself like be 2 raised to the power some order of n over c, like
Okay,
just because
so
I'm repeating.
there is just one issue here. You are repeating it multiple times. That is fine. But every time you repeat, you get different answers, right?
Every time I repeat, I get different answers. Yes, because
Between
of the
0 and 1, you
uniformity.
can get different answers, right?
Okay, yes, yes.
So from these, which answer are you picking? So if it were one-sided error, you would be right. Because in that case, the moment you get one, you are done.
Okay, okay, I get it. Like, since the
Yeah.
answer is changing, the error would also be like, maybe like not the way I'm going around.
Right. So, okay, what would the error depend on? So you have repeated multiple times, you've got an x1 to xt, right?
Right,
Now, depending on x1 to xt, you're going to make a decision whether to accept or to reject, right?
right.
So the error not only depends on x1 to xt, but the way you make that decision.
Okay,
And over here, the way we are making the decision is this, right?
right, right.
That is why we needed Chernoff bound.
Okay, okay.
Because we don't know of any, we don't know of a more direct way of arguing that the sum is at least t over 2, right?
Right, like with each, like after each number of repetitions, whether the like output remains the same or not. Like, we are not sure about that.
So I don't understand the question.
uh, like we need the Chernoff bond because like our output depends on the expectation of the input to be more than t by 2.
So, okay, the
Okay.
exact value to be more than t by 2. The
Right.
expectation would always, the expectation is always fixed,
No,
right?
no, expectation is a wrong time. I like misspoke.
Yeah, the sum,
The sum. Yes.
right?
Okay.
And we don't know of any a more direct way of bounding the probability of the sum, right?
Okay.
So over there, what we were doing was when the error was one-sided, you can think of it as picking the max or the min, depending on whether the error is towards 0 or towards 1.
Yes. Yes.
And we know how to bound the probability of max very easy. So
Sorry.
over there is a multiplication, right?
Ah. Yes. Yes. Yes.
Yeah. So yeah, what you're saying is true. It depends on x1 to xt. The error probability depends on x1 to xt in both cases.
Yes.
But in both cases also depends on the decision predicate, and these are different. So
Right.
yes, the theory has to differ.
Right. Right. Okay.
Yeah. So is this fine? Yeah. So then let's look at the next problem. So the next problem is how much space is used by the best known simulation of a non-deterministic Turing machine using Sn space by a deterministic Turing machine. The options are order Sn, order 2 to the Sn, order Sn to the 3, and order Sn square. So which is correct? The wrote something like this. Yeah, it's D.
Yeah.
Yep. Okay, so how would we prove this?
Well, it's the direct result from the Savage's theorem, right?
Okay, yes, that's one way to do it.
Okay.
So what's the proof of that?
Uh,
I
proof.
mean, do you recall it like
Yes, yes,
some,
yes, yes. I
right,
just went over it. I have some idea. Like, we look at the computation table for a non-deterministic Turing machine,
right,
and we have to find a path starting from the initial state to an accepting state,
right,
and well, in the end, it's equivalent to finding a path, the path problem,
yes.
right? And to find, just a minute. Okay. So we find the path recursively. Like suppose
Yes,
we convert this problem to finding a path in a graph, giving a starting and the final vertex S and T. So if they are same or if S is directly connected to T, we are done. That's the base case. Otherwise, we go over all the other intermediate and all the other nodes in the graph, and we check
right.
whether uh, whether well, I think we reduce the problem to going from start to T in some number of steps, I think. And
Yes, yeah.
yes, yes.
The length
So
of the path.
yes, when we are going length of the path, when we are doing recursively, we reduce the path by half. And if both of them are accepted, like from suppose S to an intermediate node we are going, and we find a path of length n by two, and from U to T we find a path of n by two, like we accept. Otherwise,
Yes,
if it's not true for any of the node, we would reject this.
right.
And showing that this takes how much space would we have to have see like what is the stack space it take, like since the problem is recursive it would create a stack of like recursive calls,
Yes,
and at each instance what are the data we are storing.
yeah. So
So
it's, yeah, it's almost exactly that. Yes.
yeah, yeah.
Yeah. So let me just quickly like recall the proof. So consider 20 TF. It has 2 to the order Sn many nodes. Um, except configuration, right? Okay, let me call this. Oh, so what we want is this. Uh, let's say C times Sn. And so what I mean by this is, okay, this is equals to 1 if and only if, right? And then as you were suggesting, we can do this recursively. So let me copy this. So this is 1 if and only if there exists an intermediate configuration D such that so a path can only exist, path of length C to the 2 to the C times Sn can only exist if there is a path of half that length from C star to D and half that length from D to C except, right?
Yes, yes.
Yeah, so space required is
How have we represented the half of the length, like c s of n minus 1?
right. So okay, so in the definition, if there is CSN over here, then it's 2 to the CSN over here, right? So when I subtract one,
Okay,
it
okay,
becomes
okay.
half.
Yes, yes, yes.
Yeah.
Sorry.
So let's say the space is S prime. Then what do we get over here? We can write a recursive relation, right? S prime of C times Sn is equal to. So for these two, I can reuse the space, right?
Yes, yes.
Yeah. So it's just one plus order Sn because that's how much I need to store D. Go over all different Ds, right?
Yes, yes.
Yeah. So when you solve this, what you would get is because I won't solve this, but what you would end up getting is this is decreasing by one, and every time this decreases by one, you get an extra order Sn, right? So how
Right.
many times do you have to decrease this? Order Sn times, right?
Orders.
Yeah, so this would be order Sn times order Sn. Because every time you decrease, you use this much extra space, right? So this is order Sn squared. Yeah. So this is fine. Okay, so now let's look at some problems related to this year's assignment, this year's week one assignment. So since the deadline for that hasn't passed, we won't look at that, but yeah, we'll look at some related problems. So first one is this.
I had one or two questions regarding the
Okay, yeah,
lectures. Should I ask it before or like
yeah,
after?
yeah. You can ask them now.
Okay, so one thing, Shahid, like in the proof for Shannon's theorem, right?
Okay,
So, like the proof exactly used in the lecture, are you aware of it? Like, or just I'll give a brief overview.
so I think what he was doing was counting the number of circuits and saying that the number of total circuits is less than the number of functions, right?
Well, that's the proof. But what he did was that for each gate, they
Okay,
were like counting the number of possibilities of like types of input. Like
right.
actually, we're trying to count the number of different graphs possible, right?
Yes.
So what was done that like for each gate, we have exactly two inputs because like we are using uh, like the
Circuits
basis is
with,
B2, right?
yes.
Right. And just to take over this. So since the size of circuit was given as S and number of inputs were N, there were
Right.
N plus S minus 1 choices for each of the input.
Yes.
So for either of the input, it's N plus S minus 1. And in B2, there are like 16 different gates possible. So that's 16 times N plus S minus 1 raised to the power 2, right? 2 times
Okay,
N plus N
yes.
minus 1, right?
Right.
And then we raised this to the power S, which is the size of the circuit or the number of gates, the internal nodes in the graph, right?
Okay.
So my question was that like when we raise this to the power S, the graph constructed would not necessarily be a directed acyclic graph, right?
Yeah, yeah. But they're only interested in the upper bound, right?
Yes, yes. Oh, yeah.
Yeah.
That's the only thing I wanted to make sure. Like,
Yes, yeah.
obviously, it includes every like directed acyclic graph, but it includes much more.
Yeah, it would include like many like okay, so what you're essentially doing is the exponent is the length of a bit string, right? That's
Exponential.
one way to think about it.
Sorry, come again.
Okay, so let's say the number in the exponent. So let's say you have s to the t, right?
Okay.
So one way to look at s to the t is 2 to the T times log s.
T to the T times log s. Okay. Yes.
And now what? This T times log s is just what you need to describe describe a circuit, right?
Okay.
So basically, given a circuit of size s, you can describe it using a string of size to T times log s, right?
Yes. Yes.
But all strings of size T times log s need not correspond to a valid circuit, right?
Yes. Yes. Okay.
Yeah, so that's another way of looking at it, that we will get all valid circuits, but we would get
Yeah.
much
Yeah.
more that's garbage.
Okay.
Yeah, but we don't care.
Yes. Yes.
Yeah,
And one thing more, like, well, I had a brief introduction about circuits in the last semester in this
complexity.
computational complexity.
Right.
Uh, you were there, I know.
Yes.
So there we didn't have the notion of formula size, like the about circuits and the formulas for a function. Right? I know the distinction from the lecture, and I haven't gone into the depth of Ayrton Shannon theorem. But
Oh,
like,
your voice broke.
I just wanted to. Sorry, am I audible now? Yeah. So just I wanted
Yeah,
to
now
know,
you're
like,
audible.
why are you going? Why are we going with this like formula size? Does it have any significance? I understand about the size of the circuit, but like, why it's important to make the uh, well out degree at most one? Does it have any relevance?
Okay, so first of all, formula is a natural subclass of circuits.
Yes. Yes.
And another is this, that, okay, in practice, when you want to create an actual circuit, you can't have infinite out degree. Because for every out degree, so okay, on every out degree, you would have some voltage, right?
Okay.
And where is that voltage coming from? Where is that current or voltage coming from? It has to come from somewhere, right? So the more out degree you have, the more, okay, so the more current the gate must supply.
Okay. No, okay, I got the practical reason for
Right.
that, but let's say like parity was being discussed in the
Okay.
first lecture, I think, no, and we made a simple circuit for it.
Hmm.
Uh, the inputs were being shared across the like AND and OR gates. The first one. Am I
Yes.
audible?
Yeah.
The screen is stuck.
Yeah. So I lost connection on my laptop. My iPad still works. Okay. Let me try to rejoin. Hmm. Can you hear me?
Sorry,
Yeah, can you hear me?
you say your voice is.
Can you hear me?
Yes, yes.
Okay, yeah. So I lost connection. I think there's some issue with my network connectivity. So I'll keep the video off for the rest of the session. Hoping this works. But you still okay? I lost the connection again. Great. Yeah, can you hear me?
Yes, yes.
Okay, yeah, so I think I'll be able to join either with my laptop or with my iPad. So, so you were asking something, like let's finish that and then I see if I can join with my iPad as well and continue. Okay.
Okay, well, you can try different IDs, like if it's a problem.
No, no, it's not the problem
Okay.
with IDs. I think there is a cultural fest in my college right now. So I think because of that,
Okay, okay.
yeah, like a lot of people are using
Okay,
internet right now, so it's terrible. That's what I think
okay,
is happening. Same with my data.
okay.
Because there are a lot of people around me, my data won't work either.
Yes, yes.
Yeah,
Got it. So what I was asking is, regarding families, formula size and circuit
right,
size, right? So we already have circuit size, and how is formula size like of some significance? Why it is more important? One thing you said was like regarding the edges, right? The number of edges, since our degree is restricted to one in a formula.
right. So that's one motivation to study formulas.
Okay, but the number of edges would remain same after all, right? Like the in one of them, the edges are being shared. Like what I'm trying to say is like let's take a simple look at the parity of two inputs
Okay.
and get a top. One side we
So
have
first
OR
of
gate,
all,
another side we have.
the size of circuit and formula can be vastly different. So for example, consider this situation. Okay.
Yes, yes, formula would be like almost every time equal or larger than the circuit size.
Yes. Yes. What I'm saying is it can be much larger because let's say you have this sub-circuit which both gates are using, right?
Okay.
This you can do in a circuit. But if you wanted to convert this to a formula, you would have to repeat this entire sub-circuit twice. Oh, wait, I
Yes,
haven't
yes.
sharing my screen, right? Yeah, so let me try to share my screen so you can see what I'm doing. Yeah, so, and because of that reason, when you try to convert a circuit to formula, the size can blow up like anything. So formula is, we
Yes, yes,
expect
like every
formulas to
time.
be a strictly weaker model.
Yes, yes, of course.
Yeah.
So why are we considering this weaker model? I think like do we have any good results or any benefits from this weaker model? Like
Okay,
that's
so
the only
that's a
thing I
good
was asking.
question. So one is
Uh,
the practical motivation that I talked about. Another is that we expect formulas to be weaker than circuits, and so we expect that we should be able to prove better formula lower bounds than circuit lower bounds, right? So that's one reason why we study circuits formulas.
okay.
Yeah, but yeah, there is not much
Right. If
difference between
we have a good
best
lower
and
bound.
lower bounds for circuits and formulas as of now.
Okay, okay.
Yeah,
Like we have some motivation, but we haven't realized it yet, right?
yeah. So yeah, true. Turns out proving formula lower bounds is also difficult. Yeah.
Okay, okay.
So can you see my screen or is it
So
still not visible?
you are presenting, but it's
Yeah,
not
okay, that's
visible
fine.
yet. Okay, it's I think. I had one more doubt, but it was like more related to computation classes. So
Okay.
I might take it at the end, if, or should I ask
You
it
can
right
ask
now
it
or at the
right now
end?
because I'm still trying to connect.
Okay, okay. So while you
Yeah.
try, I'll tell you the question. So it was like question was asked from someone else, and I tried to answer it. And I think it's from some book or some document. I don't
Okay.
know, but like the question goes like this. So if the best known solution checker for a decision problem D takes order k raised to the power n time on an
Okay.
instance of size n for a constant k greater than 1, then what is the tightest time complexity class of D according to this knowledge? Uh,
Okay. So the
should I
solution
repeat it?
checker or it's a time complexity of the solution checker or the solution finder.
Okay, so I'll say it again. We have a decision problem D,
Hmm.
and the best known solution checker for the problem takes order k raised to the power n time.
Okay. Next, so
Like k is some constant greater than 1 and n is the size.
it would be any XP.
And we have like options here like P, NP, NP complete, NP hard, and none of the others. So,
We can't
like,
say it's NP. Wait, can we say this is NP hard? Okay, so
we have options.
PNP and NP complete are not going to be true. The only thing I'm worried about is
Well,
NP
yes.
hard true as well.
Yeah, well, I tried to answer it, and
Yeah.
like it was on a forum on some Discord server. So, since the answer was already given, so I tried to arrive at it. And obviously, P, NP, and NP complete are not the answers because we
Right.
need a polynomial time verification, right? So, the
Yes.
only thing is either it's NP hard or it's none of these.
Right.
So, so since the question says like then what is the tightest time complexity class of D according to this knowledge, and what I like what my argument is like for the problem D to be NP hard, it
Hmm.
needs to be shown that any problem in NP is polynomial time reducible to this problem D.
Right.
And since the like question or the problem statement gives no evidence for this, we can't say it's NP
Yes.
hard, right?
Yeah. Yes, because
Would that work like the
yeah,
argument of
there.
reducibility?
Yeah, because otherwise, what would happen is every problem in any XP is NP hard. The issue is, I think that might be true, but yeah. Okay, so one way to prove that it's NP hard would be to prove that any every problem in any XP is NP hard.
Sorry,
Yeah, so one way to prove that the problem is
could you
NP
repeat
hard.
it?
Okay, one way to prove that the problem
Right.
is NP hard would be to prove that every problem, not in NP but in any XP is NP hard.
Mhm.
But we don't know how to do that, right?
Well, yes, right,
Yeah,
right, right.
is that's a very general statement.
So I just needed to cross check whether my
Yeah.
argument for the answer is accurate or not. That's
Yeah,
all.
so I don't think like just using what we have, we can show that it's NP hard.
Yeah, if some reduction, like it was said, like we can reduce it to say 3 sat or any problem in which is NP complete in polynomial time, then
Right.
I think it would be an NP hard, right?
Yes.
Yes.
Okay.
So do you have any luck sharing the screen?
Not yet. Let me try to switch networks, see if that works. Am I still audible? No. Am I still audible?
Yeah, yeah, you are audible.
Okay, so now I can use my Wi-Fi on my laptop. Let me try using my data on my laptop.
Why don't you try like using data on one of the devices and Wi-Fi on the other?
Yeah, so that's what I was trying. So I tried using Wi-Fi on my laptop, it wasn't working. So I tried data on my laptop.
Okay.
Yeah, but then I wasn't able to connect using my iPad. So now I'm using Wi-Fi on my laptop and data on my iPad. Let's see if that works.
Okay.
Yeah, it's iPad is lagging, but I think it's lagging.
It's like, but it's
Yeah.
okay. Okay.
Okay, so let's see how much it's going to lag. Okay, I think the lag is not terrible. It's there, it's not terrible. Okay, so the question is how many circuits of size S are there if if number of variables is n. So we saw something like this in class, and what I want to do is I want to do it in a slightly different way. Okay, Am I? Can you still hear me?
Yeah, yeah, I can hear you.
Okay, yeah. Okay, so there are S gates, and for each gate, we have three options, right? From
Like, won't the solution be similar to the proof for Shannon's theorem?
yeah, yeah. So okay, so over there we were counting circuits in one way. Here I'm trying to count them in a slightly different way.
Okay, okay.
Yeah. So over here, what I'll end up doing is I'll basically do what I told you before, right? I'm going to come up with a string which represents a circuit. That's the
Sorry,
route I'm
last.
trying to take.
Oh,
Yeah. So there are S gates. For each gate, you have three options, and so this you can represent using. Yeah. So for AND or a not, you just need two bits. And okay, so uh, for every gate, we need to specify two children, right? And this can be done using order log k at most two times. Okay, so why can we do this using at most two times log s plus n bits? Because there are s gates and inputs. So total there are s plus one many options. Sorry, s plus n many options, and uh, for each of these, like okay, so there are s plus n many options, and we can just represent this as a string, right? So we can just use a
yes,
string to index the gate, appropriate gate, right? That would
right.
need at most two log n bits. Since there are two children, it would require four log bits, right?
Yes, yes.
Okay, so so we can represent a circuit uh, a string of length s times 2 plus 4 log s plus n bits. And so there are at most 2 to the s. Yeah, so is this fine?
Yes, yes.
Yeah, so
I
what I
think.
wanted to show over here was this, that if you want to count the number of objects, one way to do it is find out how many bits you require to describe that object and then just raise that to 2.
Yes, yes. Got
Yeah.
it.
So let's look at the next problem then.
Okay, while you're writing the problem, I think the question we had for internal nodes and minus one, right? Uh,
Yes.
I think we can equate it to the problem of like what is the optimal size of like computing a circuit with. Uh, Sorry, this would be the same
Yeah, can you hear me? Did I lose connection again? Because your voice is breaking. Yes, I lost connection again.
And we have AND gates of 1 and 2, and what would be the minimum size of the circuit, or minimum number of AND gates you would need.
Oh, sorry, lost connection again. Can you start over?
Okay.
Ah, Hmm. Can you hear me?
Yes, yes.
Okay. So you were asking, were you asking something before?
Could you repeat that?
Oh, so before I lost my connection, you were asking something, right?
Yes, I was saying something that related to the internal nodes problem of tree with and leaves, binary tree with and
Okay.
leaves, right? So for the proof idea related to like what I was trying to say.
Hmm.
So I think like we can formalize the proof in the same way. The like we can say that to compute and or say or of n inputs requires
Okay.
some gates. I don't think I should say the answer or not because it's the same question is in the assignment. But like how do I state this? Like, would it be all right if I said that like it would also be the answer to the question? But
Okay, so I'm not understanding your question. So is it that
what
it's
I'm trying to
number?
say, okay, the proof we use to show that the minimum size of the circuit needed to compute and of n inputs would work same for the showing the number of internal nodes for a binary tree with n leaves.
Okay. The question is, why would this proof work
Yes. So
without like talking about the answer at all?
okay, yeah.
Yeah.
Why would this proof work, right? So well, let's look at the circuit computing and or, right?
Okay.
So each node has exactly two inputs.
Right.
Number of leaves is n, and finally there is only one output, right?
Yes.
So how do I put this formally? Uh, so each node has exactly two input. That means it's binary. There
Right.
are no cycles. It's a tree, and there are
Yes.
exactly n days.
Oh wait, why is that a tree? So if so in that question you have what's the size of the circuit, right?
Yeah, size minimal size of the circuit.
Right. So but the underlying graph would be a tree only if the circuit is a formula.
Uh, the graph would be a tree only if the circuit is a formula.
Yes. So one way to get around
Okay.
that is okay, if the minimum
Okay. Yes.
circuit
Yes.
size
Yes.
is
Yes. Yes.
n, then the minimum formula size has to be n, right?
Sorry.
So if the minimum circuit requires as gates, then the minimum formula must require as gates, right?
Yeah.
So
Yes, yes,
Basically,
right.
the circuit size is at least, okay, the formula size is at least the circuit size, right?
Formula, yes, yes, okay.
Right. So a formula would also require size S. So yes, then you can talk about the like the size of the tree.
Right, because the formula would exactly be a binary tree.
Right.
Right. So, like, but I have, so I would have to show the uh, minimum size of the formula, right?
Yes.
And well, obviously it couldn't be so. What I was trying to say that if I the proof I used to show the minimum size of the formula would exactly work for the proof to show the number of internal nodes in a binary tree with n leaves, because like you pick any binary tree with n leaves and you replace the gates with
Hmm.
the required De Morgan gates, and you'll get a formula of computing that or over n inputs, right?
Okay. So why is that true?
Pick any binary tree with n leaves.
Right. Yes. So what I'm trying to understand is how would you formally argue this?
That's the problem we started with.
Yeah. Now the problem is different, right? So how would you formally argue that given a binary tree, given a binary tree, you can convert it into a circuit. Sorry, a formula to compute OR.
Uh, the only thing like I progressed from that time was that the observation that uh, the the circuit we used to, or the formula we used to compute like and over n inputs or or over n inputs would give is exactly identical to the like a binary tree with n leaves,
Yeah, so that's one direction, right?
right?
So what you're showing is if you have a small formula, then you have a binary tree, right? But you would also need the other direction, right? From a binary tree you can go to a formula.
From a binary tree we can go to a formula. Okay.
Because otherwise, like you can have a smaller,
Okay, okay.
let's say you can have a binary tree with fewer internal nodes, but that doesn't lead you to a formula, right? In that case, you can have a smaller binary tree, but no formula. That's fine.
We can have a smaller binary tree with no
Okay, so
formula.
what you're trying to do is the following. You have okay, so you have a okay, so you know that any circuit computing OR must have size S. So it
Right,
must have S gates. And so the binary tree you obtain from that must have S internal nodes, right?
right, right.
Okay. But uh, suppose you had a binary tree with
Well,
N
this would
leaves.
all this would be true, right? Because like we said, as nodes as gates, gates are the internal nodes, right?
Yeah, so okay, this direction is true. But what I'm saying is the following. So suppose you have a binary tree with S
Mhm.
minus 1 nodes,
Okay.
S minus 1 internal nodes, and N leaves.
Sorry. And n leaves, right?
Right. Now suppose there was no way you could
Yeah.
replace the nodes with gates so that the
Okay.
resulting circuit computes an OR.
Sorry, I didn't get. Like you're trying to go from the tree to the circuit, right?
Right. Yeah, because so you want to use a circuit lower bound to argue a tree lower bound, right?
Yes, yes.
So what you need to show is if you have a small tree, you have a small circuit.
Right.
So what you need to argue is given a tree, you can convert it into a circuit.
Yes, yes. Sure.
Right. So what I'm asking is how will you formalize this?
How would I formalize this? But I have a solution. Replace all the internal nodes with the required gates. You'd get the like required circuit you are expecting, and it would
Okay,
be
right.
correct.
Okay, so but you need to tell me which internal nodes you would replace with which gates because
No, the problem is
how
simple:
would
computing and or. If I'm computing and, replace every of them with and. If I'm
okay,
computing or,
so
replace
so
all of them with all.
what I'm asking is how would you formalize that once you replace every gate with an AND gate, the resulting circuit would compute an AND of all the AND inputs.
Well, sure. Like and is what I can say associative, right? I compute and on the leaves, and then their and is computed with another leaf or like that.
Yeah, so one way to do that is using induction, right?
Right, right.
So look at the entire tree.
Mhm.
Assume that, look at the root, look at both of its children. Assume that they compute and of all of their children. So let's say,
Right, right,
look at the root in the left part of the root, the left subtree, the children are x1 to xn. In the
right,
right subtree, the children are xn plus 1 to xn. Assume
right.
by induction that both of these compute ends of all of their children,
Yes, yes.
and then argue that, okay, the topmost state must compute end of everyone.
Yeah,
Right.
exactly.
And what's the base case over here? The base case is when there is just one internal node.
And two of the inputs, x1 and let's say xi and xi plus one or something like that.
Wait, that's not the base case. Because that's one of the base cases.
The other one could be one leaf and one internal node, right?
Yeah. Okay, so the base, okay, don't induct on the number of nodes, induct on the depth.
And on the depth. Okay.
So the depth always goes down, right? Because the depth of the root, the depth of the entire tree is strictly
Mhm.
greater than the depth of both of its children, right?
Right, right.
Okay, so depth always goes down. So the argument that I had would work even with depth. Now, what's the base case for depth? The base case for depth is when depth is one, right?
At each goes by at least one
Right.
leaf.
So the base case is the depth is one, and there is just one case, an internal node.
Right,
That's
right,
the only base case route, right?
right.
Yeah, and for that you need two children, so it will compute end of them,
Hmm.
right? And now the other case, the case where you have one internal node and it is connected to the other internal node and one leaf, that is not the base case because it has depth two. So that will be covered by induction,
Right, yes.
right? Okay, so there are two base cases. No, no, the base case with depth one and base case with depth zero because a leaf is also leaf is also connected to this internal node directly, right? That's also your base case.
Yes, like if we have two internal nodes, so
Okay, so
depth
what
would
I have in
go by.
mind is this: you have one internal node, node number one, which is
Okay,
connected to node number two, which is also
okay,
internal.
okay,
Node 2 is connected to x1, x2, and node 1 is connected to x3.
okay,
Now, over here, what I want to do is I want to look at node 1, which is my root, say
okay.
its left child computes end of all of its left child computes end of x1, x2, and
Right,
its right child computes the end of x3, right?
right, right,
So, to say that the right child computes the end of x3, I need induction on, my base case should also cover the case when there is no node, right? When there is just a leaf.
right, right.
So the leaf,
That would be
like that,
itself. Like,
right. So depth zero, depth one. But depth zero is
yeah,
fine because depth one also, you can reduce it to depth zero.
yeah, yeah. Sure.
Yeah. So the base case is depth zero.
Right.
Yeah. Yeah. So using this now, I think you can convert that a proof for that to a proof for this.
Okay.
But I
So,
think, yeah, yeah. Okay. Yeah. This would work. Yeah.
so just an overall, like, how would
Yeah.
I formalize? Again, formalizing, like, what would be the overview of the proof? Like,
Okay. So the
what would I
overview
say?
would be something like this. You have a lower bound on the circuit size of any circuit which computes an AND of n
Inputs.
variables. Let's say
And
that
you say,
lower bound is S.
okay, right.
Okay. Okay. First of all, that has to be a, a size star lower bound. You need to ignore NOT gates.
Uh, Not gates. Okay.
Yeah, because a NOT gate won't fit in your binary tree, right?
Right, right. It won't be a
Yeah.
binary tree. Well, I might be wrong in this, but when I was visualizing this proof, so I assume that the circuit I'm using is not redundant, and like obviously, if I have to compute AND gates, so AND of n inputs, I'll only take AND among them, right? And I would not need any OR and NOT gate. So
Okay,
this assumption, does
so
it
you are
hold, or
using the proof in a white box way.
in a white
So
box?
basically, so you have a proof that any circuit computing AND gates must have n nodes, and in that proof you must be showing
Mhm.
that all the gates in that circuit have size are AND gates. Yes, that's
Right,
what you're using in this proof, right?
right.
Okay. Okay, so yes, if you start up with this assumption that you any uh, okay, the minimal circuit computing AND gates, computing n of n variables, must
Right,
solely consist of AND gates and
right,
has size at least s.
right.
So this is your assumption, right?
Yeah, if you take this assumption, then any such
Right.
circuit which has the required minimum size would eventually be a binary tree with n leaves.
No, 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 no. Oh, so you have this. So you have a size s lower bound on circuit, which first of all implies a size s lower bound on formulas.
Okay. Yes.
Now the underlying tree of the formula would be binary tree, right?
Okay.
Okay. So now suppose by the way of contradiction that you had a binary tree with fewer than s minus one internal nodes, but n leaves, right?
I have a binary tree with fewer than s minus one internal nodes and n leaves.
Right. So we are
Okay.
assuming, okay, so we want to prove this is not possible. So we are assuming this by
Yeah.
contradiction.
Yeah. Sure.
Right. Now using the induction on depth that we argue like discussed, you can show that this would give you a formula with s minus one internal nodes, which computes and right,
Right.
which would be a contradiction.
Okay. Yes. Uh,
Yes, so this completes the proof.
okay.
So the first stage you start off with with the assumption that any circuit must have s internal nodes. Therefore, any formula must have s internal nodes. That's step one.
Yes.
Step two is like realizing that that formula would give you a binary tree,
Uh,
and then like okay, do you need that step? Okay, no, you don't
uh,
need that step. So step one is just size as lower bound on circuit implies size as lower bound on formulas.
yes. Okay.
Okay, then uh, you start off. Step two is the following: you assume by contradiction that the circuit has the tree has fewer than tree has s minus one or less fewer internal nodes,
Okay.
and use induction on the depth that we argued to show that this tree would give you a formula with s minus one internal nodes that computes end of x1 to xn, which is a contradiction.
The last statement, could you repeat again? It's like
Oh yeah,
we assumed for like going for proving by contradiction, we assume that the tree has s minus one or less number of internal nodes, right?
right.
Okay,
Then
so
we argued that. So what did we argue by induction? That if you have a tree with
right,
s minus one internal nodes, you can come up with a formula with s minus one internal nodes that computes the end of all the inputs, right?
right.
But this would contradict the fact that any such formula requires s internal nodes.
Uh, Sorry. By induction, we are what like by induction, what we are exactly getting. Uh,
Okay, so what was the induction argument? Look at the topmost, look at the root.
right,
Both its children have fewer, have smaller depth.
right.
So by induction hypothesis, both of them compute and of all of their children, right? All
Yeah.
of their inputs,
If we go down to the base cases and like
right?
the result, how do you state the result? Like,
Okay, so the result would you can write it down in two claims. Claim one, uh,
okay,
lower bound on circuit size implies lower bound on formula size.
Lower bound on circuit size. Okay, yeah, that's the initial one. Circuit size implies on
Right.
formula size, right?
Claim two is if you have a binary tree with S prime many internal nodes,
Binary tree with S prime.
many internal
Many.
nodes, then you have a formula with S prime many nodes which compute of size S prime, which computes n. That's your second claim.
Uh, Binary tree with S prime many internal nodes. Then we have a formula of uh,
Size
what
S prime,
formula?
which computes n of all of x1 to xn.
Right. Okay. Size S prime, which
Right.
computes in. Right. Okay.
So now we have to prove this claim, right?
Yes. Yes.
This you do by induction
Then we
on
have
the
formula
depth
size S prime.
of the binary
Right.
tree.
Okay, so by induction we have proved like a formula of size S prime. We have a formula of size S
No,
prime
no,
which
no, no.
computes that, right?
Right. Okay. So if you have a binary tree of with internal S prime and internal nodes, then you have a formula of size S prime computing n of everything, right?
Okay, yes, yes.
Yeah. Okay. So
But
now, what you want to rule out? You want to rule out S prime being S minus one or less, right?
yeah, S prime can't be less than less or equals
Right.
to S minus n.
So suppose by contradiction that S prime were S minus one or less,
Okay.
then claim two would imply that there exists a formula
Mhm.
with S prime, which is S minus one or less, no size, which computes n of all inputs, right?
Right.
That contradicts claim one, which says that any such formula must have size s.
Contradicts. Okay, yes, since circuit size is S, like formula should be
Right.
greater or equals to
Yes.
S. Right.
Yeah.
Okay, so like okay, our first claim is circuit size gives a lower bound for the formula size,
Hmm.
and by induction we show that such a formula is possible, right?
Such a formula is possible under the assumption that there is a binary tree of size s prime with s prime and internal nodes, right?
Yeah,
That's
yeah, yeah.
claim two.
Okay, yes, yes,
Right.
yes, right. Okay, and if we try, uh,
Hello.
okay, yes, yes, yes,
Yeah.
yes. I
Yeah.
okay, okay,
Okay. So the second claim is if there is a binary tree with s prime internal nodes, then there is a formula with s prime size, right?
yeah, yeah, yeah. Okay, yeah,
All
and
we
like
want to do is show that s prime is not s minus one.
yes,
So now we use contradiction. So in the induction and contradiction are like completely separate. The induction is in the proof of claim two,
yes, that there exists some,
right? So
right.
that we have done. So now we can forget about induction,
Right. Okay. Yeah.
right?
I wanted to know the contradiction one. Like that's
Okay.
the
So
part
the
I think
contradiction
that's
is
missing.
this. So what does claim one say? Claim one says that any formula computing n of x1 to xn must have size s,
Right.
right? Now claim two says that if you have a binary tree with s prime internal nodes,
Right.
then you can come up with a formula of size s prime, right?
Yes. Okay.
Okay.
Yes.
So what do you want to rule out? You want to rule out S prime being S minus one or less, right?
Right.
So you start off with the assumption that S prime is S minus one or less.
Okay.
So then claim two would tell you that there is a formula of size S prime computing and that is there is a formula of size less than S, strictly less than S, computing and right,
Yes. But the first claim would contradict this.
right. So
Okay.
because you arrived at a contradiction, your assumption must have been wrong, right? What was your assumption? S prime is
Okay.
S minus one or less.
Right. Right.
Yeah.
Okay. Yes. Like then this would complete the proof, I think.
Yes.
Okay. So visualizing it was easy, but I think going through the proof is
Yeah.
much more messier. Like,
That's almost always the case.
sorry.
Yeah, that's like frequently the case.
Yes, I'm trying to
Like,
get the idea of it. Like,
yeah,
yeah. All right. Okay. So,
yeah. So,
okay,
like, we
that's
are
the
already
time.
over time. Yeah, most of the session was me trying to connect. Yeah,
Okay. Yeah.
yeah. So, if you have no more questions, we can meet next time.
Okay. Sure.
Yeah.
Uh, right. Okay. Thank
Bye.
you. Bye.